All right, let's wrap up chapter 40. So this is lecture number 4. I want to point back and refer back to lectures 2 and 3. 2 and 3 had a lot of conceptual stuff, but they also had a lot of different sorts of calculations that we can carry out in terms of energies of electrons in metals in the previous lecture, lecture 3. And then before that, the rotational and vibrational energy states. Now, if we go all the way back to lecture 1 was looking at a number of different sorts of models for chemical bonding in molecules. And there's a lot of really interesting stuff in there. Not as many applications, though. So let me just point that out. Also, in today's lecture, in lecture 4, there won't be as much in terms of applications. So for chapter 40, probably the bulk of the applications and bulk of the homework problems, if you look at them, are coming from lectures 2 and lecture 3. But let's continue on here. So we had just taken a look at energy bands inside metals and other materials also. So this is not exclusive necessarily to metals. Metals are a good example of this. But we said, okay, here is, anybody have a good guess as to what element this is? So 1s, that's the first row of the periodic table, takes us to helium. 2s, 2p, that's the second period, that would take us all the way to neon. And so we're down on the third row. I'm guessing this is sodium? It's sodium, right? 1, 2, 3, 4, 5, 4, 10. Yeah, it's sodium. So this is the electron configuration for sodium. And what we're seeing for sodium, sodium's a metal. Now, you don't go to the hardware store and ask them for a block of sodium because while it's a metal, it's also extremely reactive. So if a block of metallic sodium encounters water or oxygen, there are these violent reactions. But we can still study this in vacuum or whatever. We can study the properties. And if you look online, you can probably look up images. You can look up pictures of metallic sodium, a block of sodium metal. And what it's saying is, even though the 1s and the 2s and the 2p are thought of as core electrons, there's always going to be a little bit of overlap with the wave functions of neighboring atoms. So we could take the extreme view and say that everything is in terms of different bands of energy states, different bands of wave functions. And so if we do that, we would have a 1s, a 2s, a 2p, and a 3s band. The 3s band would be half filled because each individual sodium only has one 3s electron. And that would make it the conduction band. So this would be the conduction band, and metallic sodium is very conductive. So it's a very good conductor. The electrons can easily move back and forth between energy states on either side of the Fermi energy. Now these other bands don't contribute to the overall conduction properties because they're filled. Everything's completely filled in each one of the other bands, and so they've drawn these as a series of distinct bands. Now, I don't know the exact details on this. I would need to go back and check. But my guess is there's a good chance that there's actually overlap between the 2s and the 2p bands. They're not going to be distinct, like we mentioned at the end of last lecture. Probably the 2s and the 2p overlap. I'm not sure. You could look that up for sodium and find out what researchers, if they have evidence for one model or the other. Now, in terms of conduction, here we go. So let's take a look at that conduction band in something like copper or sodium we had just looked at. And we said that for something that gets classified as a conductor, it's got a half-filled band. And since there's a band of states very close to each other in energy, the electrons can move easily back and forth between states above and below the Fermi energy. And that makes them good conductors. Now, those are thought of as classical conductors. Here's an insulator. An insulating material has the, if we look at the outer bands, the outer band is completely filled. Now this is referred to as the valence band. Those are the electrons that are holding everything together. But since the valence band is filled, in a sense, this is both valence and conductor band. Since the valence band is filled, the conduction band, or a band that would enable conduction to take place, is at a higher energy. And in an insulator, there's a large energy gap. And so that says, hey, the energy gap here is really large. If this wants to conduct a current of electricity, think diamond, can I take a piece of diamond and conduct electricity through it? And probably not. There's probably a sizable energy gap between, or glass or something like that. There's a sizable energy gap between where the electrons have filled one set of states up to the next state that would enable conduction to take place. Now there's a series of, there's a classification of materials that are called semiconductors, and semiconductors have just continue to be very important types of materials that we use in electronic devices. Semiconductors have this interesting property of they've got a filled valence band, but the conduction band is not extremely far away. There's a relatively small energy gap. So we can actually use tricks. Now, kind of the most commonly thought of semiconductor is silicon. There's also, carbon is considered a semiconductor, and germanium, some of these other related elements to carbon. We can play around with these materials. We can take silicon, for example, and put little bits of other elements in there and create intermediate quantum energy levels. So we can create a set of quantum states that fill the gap, and then we can play kind of the game of run up the stairs. So rather than requiring electrons to transfer through this gap, which is already pretty small, if we put steps in there for the electrons, then the electrons can make smaller steps and create materials that conduct actually quite well. So silicon by itself is a semiconductor. Compared with copper, it's a terrible conductor. But with a little fiddling around with the impurities, these new versions of silicon with the impurities in place actually can become pretty conductive and have some very interesting properties for us. Now this problem is saying that it's found in some kind of a semiconductor that when we hit it with light, we hit it with photons of wavelength 345 or shorter, that's enough energy to jump the gap. So we're trying to find out how much light, how energetic are the photons coming in that would need to jump the gap. Now, visible light goes as short as 400 nanometers. So if they're saying 345 nanometers, that's off into the UV. So this block of material, I don't know if it's silicon or what, would require UV photons, probably, I don't know, 3.5 EV. We could calculate that. 3.5 EV or something would be the size of the gap between those two bands. And now, here we are back looking at the Fermi-Dirac probability function. This was what we saw back when we were looking at the density of states. So when we were looking at density of states in conductors, we were using this formula to tell us what the probability would be that a particular state would be filled with an electron. And here it's looking at energy gaps for silicon. Now, it's, here we go, here's the energy gap for a block of silicon is 1.14 eV. So that gap, that's not so large. 1.14 isn't UV, that's infrared actually. So kind of a fairly energetic infrared photon would be enough to boost an electron into the conduction state for silicon. Now it's saying that zinc sulfide is about 3.6. That looks more like that example of requiring UV light to be able to boost the electron into the higher state. All right, semiconductors and doping. So we talked a bit about taking silicon and putting impurities in and creating a piece of silicon with other materials in it is called doping the material. And the most common semiconductors that we use are silicon and germanium. A tiny amount of an impurity, a tiny amount of doping, can increase the conductivity quite a bit. Okay, so that's what we are looking to do here. And so here's a couple of examples of doping. What it says is that we have silicon, which is silicon's got 4 electrons in its p shell, in its S and P, out of its octet, it's got 4. Arsenic is an N-type semiconductor. Arsenic is 1 column over from silicon, and arsenic is going to have 1 extra electron. So here is pure silicon, and here it is showing, so this is kind of a diagram here. There's 4 electrons that silicon has in its outer layer, 4 valence electrons, the same as carbon, and that it can share those electrons with neighboring silicons and form these pairs of electrons that are forming chemical bonds. Now, the arsenic atom, if we put arsenic in, well, arsenic ends up sliding into one of the locations where there would have been a silicon otherwise, and that arsenic has an extra electron that comes in. And what we're going to find is that creates a disruption in the energy levels of our bands that we can begin to generate quantum states inside the gap. So we can get quantum states for these electrons to fill these gaps. Another example, here they've used gallium as an impurity or as a doping material. Now gallium is 1 column to the left of silicon, and that says when you get a gallium substituted in to this location, there's going to be what's called a hole. So there's a missing electron at that location, and we find out that can also create intermediate wave functions. It can create quantum states within the gap that we're trying to jump through. This picture is trying to point out, so in solid state physics, in condensed matter physics, there's a lot of discussion about holes where there's a state without an electron. That's referred to as a hole. So it's a vacant state. And we even talk about holes moving from place to place. If an electron from here moves over into this quantum state, it opens up a hole over here. So we can either say the electron has jumped from here to here, or we can say the hole moved from one location to another. I can't get used to that. I still have to think in terms of the electrons actually moving from one space to another. But it's very common discussion to say that we have these holes moving around within the semiconductor material. All right, so here they are side by side. Here is the N-type semiconductor material. Here is the P-type. N meaning that we have an extra electron, which kind of stands for negative. And P-type meaning that we have a missing electron, and so we write that as P. Now they're not really positive and negative, but those are the types of doping materials that we have placed inside these materials. So, so let's see what's happened here. So in pure silicon, we had the valence band here, we had a conduction band here, valence band here, conduction band here. But when we added in this case we put the arsenic in there, what we did is we generated a new set of quantum states within the gap. Now, what happens is we created a set of quantum states just below the conduction band, and we brought electrons to fill them. Now, since the valence band is already completely filled, those additional electrons brought in with the arsenic have to go into the new set of quantum states. And since those new set of quantum states are within the gap, it's a much shorter jump to move into the conduction band states. So this came in with these donor level quantum states filled with electrons, and for some reason this chart is showing all the electrons are here in the conduction band. Actually, they can just jump back and forth. So they can jump between that donor level into the conduction band back and forth, and that allows movement through the material. So that was doped with arsenic. Now let's see what happens if we use a p-type semiconductor material. If we use a p-type semiconductor material, we also generate some quantum states that are here, but these quantum states are taking the place of quantum states that used to be down inside the acceptor level. So what we've done here is create an additional set of quantum states that enable electrons to jump in and out of the valence band. So that works too. We can also get conduction by having electrons jump in and out of this intermediate state that we've generated, putting a little bit of doping material inside. So, so this becomes really useful. Depending on how much impurity we put in, we can create different numbers of states, and we can develop different conduction properties for these materials. I am not going to worry about that slide. I'm going to move on to diodes. Semiconductors, so diodes are kind of the simplest device, electronic circuit device, that are based on this idea of using different materials with different doping properties to them. So here we've got a battery set up. Here's the plus side, here's the minus side. We're going to try and drive current through this diode in this direction. So we're going to this is where I actually have to stop thinking in terms of current and think in terms of electron flow. So what's happening here is this is conventional current flow. Electrons are coming from the negative terminal, and electrons are being pulled into the positive terminal. So what happens, we're going to put a p-type material here and an n-type material here. And what that does is it draws electrons out of the quantum states in the valence band and in the acceptor level. And that enables electrons from here to jump the boundary. So those electrons now can jump the boundary over to the other side fairly easily, and so we can have a flow of electrons in that direction. Now let's take this diode out and just flip it over. So no, they flipped, sorry. We're going to keep the diode where it is. We're going to flip the voltage source. So let's take the battery out, flip it over. Now, if we take the battery out and flip it over, now what we're trying to do is we're trying to push electrons into this positive state. Now, if we go back and look how this is set up, what we're trying to do is push electrons into here, and that doesn't help. It just fills in the valence band, but there's no easy quantum states over on the n-type material that enable those electrons to cross the boundary. So here is the boundary for our diode. It's got a thin layer of n-type and a thin layer of p-type pushed together. And let's just go back and review what we saw in that other one. So when we try and push electrons in from this direction, the electrons coming in are filling this donor level, and a bunch of electrons filled in this donor level can easily drop into available quantum states on the other side of the boundary. So I have this very easy electron flow from the N-type over into the P-type material. Going from N to P for the electrons, no problem. But when the electrons come in through the P-type, they end up in these lower energy states. In order to conduct, they would need to jump up into one of these conduction states. That doesn't happen. Now, if we put a diode in a circuit and we drive enough voltage, we can force the issue. But under normal operating conditions, diodes are designed with these properties in mind, where going from N to P for the electrons, no problem. Going from P back to N for the electrons, that just doesn't happen. And what that does is it means that the diodes are a one-way switch, which is actually pretty interesting, right? If you've got a very simple device and it only enables current to go in one direction and blocks it from going the other direction, there's a number of uses we might think of for these diodes. So let's take a look at some of these and see what we have. So this is just outlining what we've just talked about. So here is the conduction band, here is the valence band. The question becomes, how do we get the electrons to cross this gap and become more conducting? Now what I did do in drawing this picture is I went back, there was that earlier slide that talked about photons of 345 nanometers. I thought this would be a good place. I calculated that. It was about 3.5 or 3.6 eV. So that's sizable. That's a lot of energy for an electron to overcome in order to be conducting. So this doesn't, I don't know if that's a semiconductor or not. That's actually a pretty good sized gap. Okay, put that to the side. Get back to the diode story. So here's the N-type material, P-type. And again, what's going to happen in a diode is if we push electrons into the N-type, they're going to go into these donor quantum states, and from there they can cross the boundary and easily drop into the acceptor quantum states, which have been opened up. So the P-type is attached to the positive terminal. The positive terminal is pulling electrons out of these lower states, where the N-type is seeing electrons coming in to these upper states. If we reverse that, if we try and push electrons in from the P side of the diode, then in this P-type material it fills up these acceptor levels, doesn't really put anything into conduction, and from the acceptor level there's still a sizable jump into the donor level. So conduction doesn't work very well. So at least in the forward direction, when we look at current as a function of velocity, what we see is as the velocity increases, the current goes up, well, kind of a theoretical prediction is it goes up exponentially. So it's not Ohm's law. You know, a standard resistor in a circuit produces a linear response. If we double the voltage, we'll double the current. But this is not a standard resistor. This is a diode. And for the diode, as we increase the voltage difference between the two sides, so what we're talking about is putting a voltmeter, one of the contacts here, one of the contacts on the other side of that diode. As we increase the voltage, the current increases exponentially. Okay. And then we use that understanding to design different types of circuitry. And here's a more detailed picture. So there is the exponential takeoff in the forward direction. Well, what does happen if we try and drive this with a large voltage in the other direction? And in what's called the reverse bias, this is showing for this particular diode that they've been looking at, it takes 12 volts. At 12 volts, we can force the issue and drive current backwards through this diode. But up to, almost 12 volts, it's a pretty good gate. It's not letting the current go in that opposite direction. Whereas in the forward bias, what we're seeing is even getting up to a few hundred millivolts, we're starting to see current start to really take off. Now here's an example that they have. You could take a look at this if you want. This is really optional for you. But in any case, this is a problem with a battery and a resistor and a diode. And looking at what the properties are going to be. All right, here's one of the really handy uses of diodes. Let's say this. Let's say that we have some kind of an AC source. Maybe it's just an AC a voltage source, like plugging into an outlet. And here's a diode set up here. Now, what's happening here is they're doing a comparison as to what's the voltage of the source. So here's our voltage source, and the voltage source, it's an AC generator, and it's an AC generator that has a nice sine function pattern to it. Well, what happens if we put a diode in here? Well, whenever the current is going in this direction, current flows. But whenever the current's going the opposite direction, current shuts down. So instead of getting the full effect of the AC, what we've done is we've limited the voltage, the current, to only be in one direction. Now, what they're looking at is if I put a voltmeter out here, if I now connect a voltmeter to points A and B, points A and B are going to be measuring the voltage across that resistor. When there is current flowing, there's going to be a measurable voltage, but when the current shuts down, this voltage will drop back down to 0. Okay, and so the voltage that we start with looks like this, and what we've done is we've eliminated any of the voltage in the opposite direction. So that's called a half-wave rectifier. Rectifying meaning we're taking something that's going in both directions and we're limiting it so that it only goes in one direction now. And diodes would be ideal for that. All right, here's a circuit that's a little more complicated. We've got an AC source, and then we have a transformer set up here. So here's an AC source. Let's say this is something you've plugged into. So this is a power supply or something. You've plugged that into a wall outlet. That wall outlet is an AC source. Here is a transformer, which is going to change your voltage. And then what we've done with this transformer is we've grounded the center portion of the transformer. Now, this is actually how houses are hooked up. There's a neutral wire inside the wiring inside houses, and it actually has to do with, it's set up like this, and then you end up in standard electrical hookups for houses and buildings. You have 120 volts here, you have 120 volts here, across here you have 240 volts. So the transformer itself is set up to enable a difference of 240 volts. So those transformers up on the power lines. And then the 3 wires coming into your house are these 3. So there's a neutral line, there's a hot line, and there's another hot line here. And if I connect up circuits using the ground and one of the hot lines, that's 120 volts, or I can do the same thing here, I get 120 volts here. But if I use these two, those are the lines we use to set up 240 volts in our house. Anyway, just a quick aside from Physics 4B. Now what we want to do is we want to take these diodes. Now what's going to happen here with this circuit is I'm going to have current going one direction and then back the other direction. And it's going to oscillate back and forth. And if this is a standard electric hookup, it's going to be oscillating back and forth rapidly. It's going to be oscillating back and forth like 60 times a second. Now, what's going to happen then with these circuits is that when the current's going this way, I will get a contribution from here. And so that can continue into the rest of the circuit. Now, there's a capacitor, and if you guys remember from Physics 4b, capacitors store charge. So when the current becomes really high, some of that gets stored in the capacitor. When the current drops off, the capacitor releases that. And then we have an output. We have a resistor here also, and then we have an output. Now what's happening is, going back to our diodes, so this diode is allowing the current to go this way and complete through the rest of the circuit. The return for the circuit is through the grounding effect. So if this has been connected to ground and this is connected to ground, well, that could be a physical wire that is actually used in household electricity as a ground wire or a neutral. There's a physical connection between those. Or it could also be that there's just some copper, big pieces of copper pounded into the ground, and it literally is a ground, meaning that this electrical connection between these two is to be carried out by the ground, by the earth. The rest of the conduction will travel through the earth itself. All right, so when the current's going this way, the circuit's completed through here, and then when the current reverses, the current goes this way, and the current is completed through here also. So what that's giving us is it's taking something where we have the effect of the diode. So what the diodes are doing is it's allowing the AC effect to still take place, but it's only allowing the current to go in the forward direction. Notice that when we look over onto this part of the circuit, the capacitor, the resistor, the output, the current's only going one way. And it only goes one way because whenever the current tries to go backwards, it runs into a diode. So we start off with the AC. That was not shown here. The presence of the two diodes gives us a fully rectified output. And then the presence of the capacitor smooths that out. So this is what happens in going from an AC to DC converter. If we have an AC source, but we want a DC power supply, we can take a transformer, run it through a rectifier, which is some number of diodes, and this is not the only possible configuration. And then we can use some big capacitors, relatively big, to smooth out that effect. And then you can get to where you have a pretty smooth output, right? Some bigger capacitors here, and maybe we've got a pretty flat line in terms of the voltage output. So diodes are really handy. Diodes show up in converters. Now the other device that we hear a lot about besides diodes is we hear quite about, a bit, I'm going to guess, about transistors. So transistors and integrated circuits. Transistors, instead of 2 layers of doped silicon, they have 3. So instead of just an N and a P like the diode, they have an NPN, and they have a PNP. So this is an NPN transistor, or the other possibility here is a PNP transistor, and they both become important switching devices. And by switching, what I mean is this. Let's look at the NPN here. If we have an emitter, now the emitter on these is where we think of, for me, I'm going to think of the electrons coming in. So here are the electrons coming in to the emitter, and the question is, where are the electrons going to leave? Are the electrons going to leave through the base? Or are the electrons going to leave through the collector? So it's kind of like I'm coming into this transistor and I've got 2 possible exits. And what we can do is we can control what fraction of the current goes out through the base and the collector by making small voltage changes. So what's happening is, and we'll take a look at the quantum states here. I guess we're good on this. Now, PNP transistors are thinking in terms of vacancies or holes in the quantum states. So in this case, It's more as current coming in here and leaving in terms of they're actually coming the other direction. So the current coming in here, and then how much additional current comes. It's kind of the reverse of this. So for myself, I always prefer starting thinking of what the electrons are actually doing, and in the MPN, that's easier to see. This is kind of the reverse effect. Let's go ahead and look at those diagrams. Here we go. So here's an NPN transistor. Here are the electrons coming in through the emitter. They're coming in through these donor levels. Now, here are the two options that they have. Clearly, there's a piece of P-type material sandwiched in between the N-type materials. And this P-type material has these acceptor quantum states just sitting there, waiting for the electrons to drop. But the other option that the electrons have is, oh look, there's another set of, there's another layer of N-type material, and it's not really ever so far away. I could jump the P-type material and go right over to the N-type. I could tunnel. So depending on how wide we make this piece of material, and depending on what voltages we have across the base versus the collector, we can draw more of the electrons into the collector donor state versus the base. So again, what we can do is we can design these transistors in a way where we can switch the electron current and decide which direction and what fraction of the current is going to go in either particular direction. And here's, and we're not going to look at any detailed examples of this. There is a homework problem that I listed. If you want to take a look at it, that's really up to you. But what we've got here is we've got a circuit. Here is a signal of some sort. So I've got a battery here, and the signal or the current in here is being modulated by some kind of an input signal. That's coming into the base. And so what happens then is there's a small amount of current, or there's small variations of the voltages in the base. And what I'm also doing is I'm running this amplification circuit over here. So I've got this small, very modest signal coming in, and then what I have is this large voltage over here driving a lot of current. And I can use the small variations in the base to create a signal in this other circuit, and the signal in the other circuit is amplified. Since I'm running, 10 times or 100 times the current over here that I'm running over here, this current, the pattern in this current, is going to be modulated by whatever's happening in that fairly weak signal coming in. So this transistor has now created an output that, maybe it's 10 or 100 times larger than the signal that came in, and it still carries the same pattern to it. So again, something like an amplifier can be set up by using the properties of our transistor. All right, so we're going to wrap it up here. So this is our summary of Chapter 40. So what we've got here are, we looked at molecules early on. We talked about covalent and polar covalent. And then we said in the extreme case, if the covalent bond becomes so polarized that the electron pair is pretty much shifted to a large portion to one of the other atoms, we start referring to those as ionic. Now ionic typically means it's become so polar that when we put it in water, the bond comes apart. Okay. Then we move on. And look at electron wave function overlap as a way of forming these types of bonds. Now we said that even once kind of the bulk of the chemical bond has been formed, because of quantum effects, these electron densities are shifted in a way where you get polar chemical bonds. If the bonds are polar in nature, then that means that there are going to be leftover positive and negative charges that will continue to attract each other. The example we saw with this, we looked at those DNA molecules and the individual bases and saw that they still attract each other. And when the individual bases in the DNA come together, you know, it's a tenth of an EV or something in terms of energy released. Energy levels in molecules are altered. Okay, so energy levels in molecules, we've got rotational and vibrational states, and we went in and that's something we took a lot of detailed look at. And then we looked at metals and we looked at closely spaced bands. These seem like they're a little bit out of order. The rotational energy levels are quantized. We certainly took a look at that. Vibrational energies are quantized too. Those are the two I was looking for. Rotational and vibrational energy levels are quantized. If you look at the homework set, you'll see that the bulk of the homework problems are looking at rotational and vibrational energy states, as well as looking at metal bonding. Crystals and conductances, so the band structure, so we've talked about the band structure. And then our discussion on semiconductors, how diodes operate, how transistors are going to operate. All right, so that takes us through lecture 4. That takes us through chapter 40. So we are pretty much through chapter 40. And again, if you guys have questions, let me know.